Hey class, this is going to be lecture 31, which is the last lecture before exam 3. So this is the last of the material that you'll have on exam 3. And then after this, I'll post a exam 3 review that will go over exactly what's on the test, just like I've done for the last 2 exams. All right, let's get started with the PowerPoint here. Okay, today we're talking about acid strength. Last time we talked about how to determine if something is an acid or a base, and then how to name it. And today we'll talk about acid strength. So we'll start with just this review quiz from the last lecture. So go ahead and pause the video and try this out. Okay, so it says, what is the conjugate acid of carbonate? Okay, so if the question's asking for the conjugate acid of carbonate, it's making the assumption that this is the base. Okay, so a base being converted into a conjugate acid. And remember, bases accept protons. So if carbonate accepted a proton, it would become HCO3 minus. Okay, so that would be your conjugate acid. Okay, so again, the conjugate acid is always just whatever the base is plus 1 proton. Okay. And then for if the question's asking for a conjugate base, it's going to be whatever the molecules it gives you is going to be the acid, and then you take away a proton to get the conjugate base. Okay. All right, and then we'll go ahead and try this quiz. If you didn't do any of the reading or anything beforehand, you might not know the answer to this one, but you could attempt to answer it here. Okay, so the question says a strong acid is one that blank. And the answer for this is going to be dissociates completely. And we'll talk about which acids are strong acids, which bases are strong bases, and relationships between those throughout this lecture. Okay, so I'm not going to be doing this demo, but the information on the slide is still really helpful. So again, according to the Arrhenius definition that we covered in the last lecture, acids and bases are electrolytes, right? Acids produce H plus ions and bases produce OH minus ions. So electrolytes are anything that produces ions in solution, right? So strong acids and bases are going to dissociate completely, and so they're strong electrolytes, right? Because strong electrolytes dissociate completely, okay? And then weak acids and bases only dissociate a little bit, and so they're going to be weak electrolytes. And there's just some examples there, but don't worry about those too much. We'll talk about how to know if something's a strong or a weak acid. Okay, so a strong acid, if you just looking at this graphic here, shows you that initially, let's say we have HA is going to represent our acid. And after it's placed in water, you have all of these hydronium ions and the conjugate base, okay? So you don't have any of the acid left initially. It all completely dissociates into hydronium, or you could just say H plus, and conjugate bases. So that's the definition of a strong acid, where it dissociates completely. Looking at a weak acid, let's say you have just acid present initially, and then after the reaction, a little bit of this acid dissociates into hydronium or H plus ions and the conjugate base, but you still have a lot of the acid present, right? It didn't fully dissociate. That would be a weak acid. And we've seen this before with electrolytes too. Strong electrolytes dissociate completely, weak electrolytes dissociate slightly, okay? Okay, so the way to know something is a strong acid is just, unfortunately, to memorize it. So there are 6 strong acids that you need to know, and they're on this chart. And then anything else is going to be a weak acid. Okay, so that's how you know if something's a strong acid or a weak acid. It's strong if it's on this chart. If it's not on this chart, we're going to call it a weak acid. Okay. Okay, so here's some examples of weak acids, but again, anything else that's not on the chart is going to be a weak acid. So for strong bases, they're going to be group 1 and group 2 hydroxide. So those are elements in the first or second column on the periodic table, right? So lithium, sodium, potassium, rubidium are all on the first column of the periodic table. Magnesium, calcium, strontium are going to be the second column of the periodic table. Whenever those are paired with hydroxides, those are strong bases. And again, strong bases and strong acids are both strong electrolytes and completely dissociate when placed in water. And then again, if the base that you see is not one of those strong bases that we talked about, pretty much all the other bases are just going to be weak bases, okay? As far as we're concerned with in this class. Okay, so generally bases that don't have hydroxide are going to be weak as well. But as far as like understanding what's a strong base and what's a weak base, I'm only going to like require you to know the strong bases, which are the hydroxides paired with the group 1 and group 2 elements. Anything else, you could just say it's a weak acid, or sorry, weak base. Okay, so here's some examples. So in this example, we have ammonia, okay, and it's going to accept a proton and become ammonium, right? And so that's a base, and in this case, it's a weak base because it's not one of the strong bases. Fluoride as well is going to take a proton and become HF, and it's going to be considered a weak base because it's not one of the strong bases that we talked about. Okay, sounds kind of silly, but I think it's the simplest way of understanding what's a weak base and what's a strong base. Okay, so we have some charts that you'll see that show acid strength and base strength. And so really there's kind of a spectrum, right? It's not like it's just strong acid or weak acid. We kind of make these artificial lines and say like these are strong acids and everything else is a weak acid. But the truth is there's, it's really a spectrum of strong to weak acids. And we'll talk about how to know exactly how strong or how weak an acid is. How strong or how weak an acid is. But one thing I wanted to show is that acid and base strength are inverted basically from one another. Don't know if that's the best word, but so for example, let's look at the hydronium ion, which is H3+. This is increasing acid strength, so this is a pretty strong weak acid. This is a table of weak acids. None of these are on the strong acid list. But as far as weak acids go, hydronium ion is a pretty strong weak acid. Sorry, hopefully that terminology is not confusing. But anyway, the strength of hydronium is pretty high. And the conjugate base of, so this is the conjugate base of hydronium. So the stronger the acid is, the weaker the conjugate base would be. So you can see hydronium ion is pretty high as far as acid strength goes, but the conjugate base of hydronium is water, and it's very weak as far as base strength goes. Okay, let's take something kind of right here. So bicarbonate is a pretty weak acid, but the conjugate base of bicarbonate is carbonate, and that's a decently, it falls kind of right here, I guess, on this arrow. It's a decently strong base. Again, the main idea to glean from this slide is just that the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base will be. And that should make sense. For example, if something is a strong acid, so let's just say like you have this acid HX, put it in water, and you get X minus plus H3O plus. Okay, so if this is our acid that we're looking at, if it is a strong acid or a stronger acid, it's going to want to give up its proton, right? The strong acids dissociate. So if it really wants to give up a proton and become this, in the reverse direction where it's acting as the conjugate base, it doesn't really want a proton that bad, so it's kind of a weaker base, right? So that shows how like the stronger the acid is, the weaker the conjugate base. Okay. Polyprotic acids. So polyprotic acids are acids that have multiple hydrogens to give up. Right, an acid donates a proton. So something like sulfuric acid, it could give up a proton and become hydrogen sulfate. Hydrogen sulfate can then go on and give up another proton and become just sulfate, right? So this is referred to as a polyprotic acid. Each additional hydrogen that is weaker than the last one. So what that means is sulfuric acid is a strong acid, and then after it gives up a proton and becomes hydrogen sulfate, it's still an acid because it can give up a proton, but it's a weaker acid than it was before because it already lost one of its protons. Okay, same with phosphoric acid. It's going to get weaker and weaker as it gives up protons. That's just kind of the idea to pull from this slide. Okay, so now we get to this question that says, how do we know which weak acids are stronger or weaker than others? So we talked about how in that list of weak acids, there's kind of a relative strength distribution. And we need something that tells us how strong or how weak an acid is. So we're going to use an equilibrium constant. So we're pulling in an idea now from what we've learned before with solutions and applying it to the acids. So if we look at this very generic acid reaction, you have an acid, HA, okay, that's going to give up its proton, and this would be the conjugate base, okay? So if we wrote the equilibrium constant expression for this, we would have the concentration of hydronium times the concentration of the conjugate base over the concentration of the acid. We exclude water here because it's a liquid, right? And so it's excluded from the equilibrium expression, constant expression. Before we've used Kc, this is going to be Ka. It's kind of the same thing. It's just applied to the acid, so we use an A here to say that. So it's called Ka. And so if the Ka is large, we have more products, right? So we talked about if Ka is large, or before we talked about if Kc is large. But if K is large, we have more products. And if we have more products, that means our acid dissociated more. So if the acid dissociates more, it's going to be a stronger acid. If you have a smaller Ka, there's fewer products, and it's going to be a weaker acid, okay? And the smaller and larger is when you're comparing two different acids. So if you're looking at two different acids, each acid is going to have its own unique Ka, and the one that's larger is going to be a stronger acid for all of these reasons here, okay? So here's a table, for example, that has a bunch of different acids and the Ka listed. So you can see the larger the Ka, right? This is the largest Ka, and then the Kas get smaller as you move down. But as the Ka goes bigger, as the Ka gets bigger, the acid strength increases. Okay. So hopefully that makes sense there. All right, I'm just pointing out the different polyprotic acid strengths here. Okay, now we're going to talk about base strength, and we compare this in a very similar way. So this is a generic base reaction. So here we have our base. It's going to accept a proton, and this would be the conjugate acid. If we write the equilibrium constant expression, we'd have the conjugate acid times hydroxide concentration over the base concentration. Large Kb means that your base is going to be picking up protons more and forming product. So larger Kb, more products, is stronger base, similar to the Ka. You're often only given Ka, and so there is a relationship between Ka and Kb, and that is Ka and Kb of a conjugate acid-base pair. And we'll talk about that in a sec. But the relationship is Ka and Kb for any given conjugate acid-base pair is going to equal 10 to the negative 14. and that's just a number that we need to know. This is also sometimes referred to as kW, and I think this constant might actually be on your equation sheets, but I would double check that. And you can rearrange it. And so if you're given Ka, you're often going to use this relationship here. This is just this expression rearranged. So if you're given a Ka, you can figure out Kb for any Ka. Okay. This also shows that Kb and Ka are inversely proportional to each other. So if Ka is large, you're going to have a small Kb, which again goes along with the idea that the stronger the acid, the weaker the conjugate base. Okay. So let's go ahead and try this quiz. So the question says, which is the stronger base? And this is often what you'll see. You'll have a table of Ka values. Okay, and even if the question asks which is the stronger base, you're going to have to use the Ka values. So you're going to have to convert Ka to Kb in order to solve this question. Okay, so we need Kb for F minus. Okay, so if F minus is our base, again, to get Kb using Ka, we need to find the Ka of the conjugate acid of F minus. Well, the conjugate acid for F minus is just going to be HF, right? It's a conjugate acid. So we need to pull the Ka for HF, which is right here. The conjugate acid of cyanide is going to be hydrocyanic acid, right? So it's just the base plus a proton, and the Ka is here. So then what we can do is, for example, for F minus, to find Kb, we'll take the Ka from the conjugate acid, which is 7.2 times 10 to the negative 4. Plug that into our equation, and this gives us the Kb for F minus. And then we would do the same thing for cyanide to get the Kb for cyanide. Okay, and now we can compare Kb's, which makes it a little easier to see. And we can see that the larger Kb, which is this one here, is going to be the stronger base. Okay. All right. All right, go ahead and try this question here. Okay, so this question says, without using any math, which of the following bases is the strongest base? So of course, on a test, I wouldn't know if you use math or not, so you could answer this however you wanted. On a test, I'd probably just say which of the following bases is the strongest base. And we're giving Kas. So you could look at the conjugate acids of all these. So for example, the conjugate acid of carbonate is bicarbonate. And I'll just list the different conjugate acids here. You could then look at the Ka values, calculate Kb, and then compare all the Kb values for these bases and see whichever has the highest Kb would be the strongest base. Another way to do it is just to remember that Ka and Kb are inversely proportional. So whichever conjugate acid has the lowest Ka means that the base would have the highest Kb. Okay, so if we look at carbonate, right, this is the lowest Ka, so that means that CO3 would have the CO3 2 minus would have the highest Kb, so it would be the strongest base. All right. Okay, so again, we can just use this chart to show the inverse relationship between acid strength and base strength. So if an acid has a large Ka, its conjugate base would have a small Kb. Okay. All right, go ahead and pause the video and try this question out. Okay, so this says you place some nitrous acid in water, and measure the ratio of nitrite to nitrous acid to be 0.007. What is the concentration of H3O plus, so hydronium, in solution? Hint, use the formula for Ka. Okay, so nitrous acid, if you are stuck here, you first need to know what nitrous acid is. And so nitrous, remember, us acid is when it's the ITE form. So nitrite is NO2 minus, right? Oh, I guess it gives you it right here, so you don't really need to do this. But anyway, if you didn't know, that's how we got nitrous acid here. and you measure the ratio of nitrite to nitrous acid to be 0.007. Okay. So let's now write out the formula for Ka, because that's what the question kind of hints that we should do. So Ka is going to be products over reactants, right? So let's look at what the equation would be. It says you place nitrous acid in water. So let's just say we have nitrous acid, we put it in water, okay? So since this is the acid, it's going to lose a proton, become nitrite, and then we would have H3O plus, right? Okay. So if we wrote out the Ka, we're going to have the concentration of nitrite times concentration of H3O plus divided by the concentration of nitrous acid. Okay, it wants us to calculate the concentration of H3O plus. Okay, well, we know Ka because we have this table here. So if we find nitrous acid, that's right here. So we can plug in our Ka value. So we have 4.5 times 10 to the negative 4 equals this. And we're not given individual concentrations here, but we are given what this ratio is equal to. So I could separate this out and say this is equal to concentration of nitrite divided by concentration of nitrous acid times concentration of H3O plus, right? So this right here and this are equivalent. So now, since I know this ratio, I could plug that in. 4.5 times 10 to the negative 4 equals 0.007 times the H3O plus concentration, right? Now I can just divide. So take 4.5 times 10 to the negative 4, divide it by 0.007, and that equals the hydronium ion concentration. So that would just be putting in your calculator and doing the calculation at that point. Okay, I'm gonna walk through it here just with the PowerPoint. Very similar thing. Get your concentration. Okay. All right, that was the acid strength lecture. That's going to be the last lecture for exam 3. So make sure to practice those principles. And at this point, if you're still feeling unsure what's on the exam, make sure to watch the exam 3 review. And then if you have any other questions after that, just shoot me an email or get on office hours and we can talk about it. So, all righty, have a great day.